Can you hear me now? Okay, good. All right, any comments, questions, concerns before we start? I hope the review we had last week was helpful. And today we'll be talking about priors. So I usually break this lecture into two parts. Okay, priors. And then we'll have a lab that goes along with priors too. And I'll post that today. So we had this graph last time that visualizes the three parts of, or four parts, I guess, of Bayes' theorem and the posterior distribution, where we have a function for our likelihood. This is y given theta. And then we have a function for our prior on a parameter theta. That's this green function here. And then we have the marginal distribution of the data, just the brackets around y, which is the blue line here. And the area under this curve is how we normalize our Bayes' theorem to sum to 1. So recall that the posterior distribution represents a balance between information contained in the likelihood and the information contained in the prior. An informative prior is going to influence the posterior distribution. A vague prior exerts minimal force. And in fact, when you have very vague priors, Bayesian inference looks very similar. At least the parameter estimates look very similar to likelihood analysis. So you're likely to get the same estimated value for your parameters in using likelihood analysis versus Bayesian analysis if you have a very vague prior. Priors are optional in inference based on maximum likelihood. So we saw how we could do this in lab 3, where we can sum up the likelihood of the prior and add it to the likelihood of the data. But priors are mandatory in Bayesian inference. And this is because it's based on our rules of probability and Bayes' theorem and how we conditional joint likelihoods. Okay, this is, and the first day of class, I think I asked what the definition of a confidence interval was, and we can see how priors influence our data. So here we have the probability of a correct answer. So if you get it correct, it's a 1. If you got it incorrect, it's a 0. We have the prior distribution is around 0.2, so about 20% of people answer the definition of a confidence interval correctly. When we have a posterior distribution with a vague prior, here shown in this blue line, it looks very similar to a likelihood analysis without incorporating a prior. Now we can do, let's see, we have priors, our black line, our posterior with our prior. Here is the red line. We have a strong prior in the black line. We see the strong prior is really influencing the posterior distribution. So if we've asked this question for lots and lots of classes, eventually we're going to have a very strong prior, and the new data we collect each year for asking this question doesn't change the posterior distribution that much. But when we first start asking this question, we don't have very much data, and our posterior distribution is going to look like our prior distribution. So it's a way of obtaining information over time, and we can see how that information evolves by comparing priors past priors to our future posterior distributions. All right, so we're going to talk about informative priors, and then we're going to talk about vague priors, and then we'll talk about conjugate priors. All right, so most of the examples in the textbooks you see on Bayesian inference use vague priors. And I'd like to make a case for using informative priors when the information is available. So why would we want to use informative priors? Well, here's 6 reasons why. It's a natural way for updating analyses. So if you are doing a study each year, you're collecting new data each year, and study design is very similar. When you obtain new data, you can obtain your new posterior distribution. And then in the following year, you can use that posterior distribution as your prior distribution, and then again, obtain new data and update that posterior. So it's a natural way for our understanding of parameter estimates to evolve. Another pragmatic reason for using informative priors is that it really speeds convergence of our Markov chain Monte Carlo algorithms. There's less space that the algorithms have to search over when they're trying to find what the true parameter estimates are, if we can use those priors to help that. And we'll see that and how that helps when we actually get into programming MCMCs. It reduces problems with identifiability. When we use logistic regression, mainly logistic regression or anything with a link function that links a linear model, beta 0 plus beta 1x plus beta 2x, to 0, 1 data, there's often issues with correlation in the parameters. And we'll talk more about identifiability, but the idea behind identifiability is similar to an algebra when you have 3 equations or 3 unknowns and only 2 equations. You can't really figure out what each one of those unknowns are if you only have 2 equations. It could, if you increase one, it could be another one. We'll talk more about that. It allows estimation of quantities that would otherwise be inestimable. So if you can choose reasonable values for parameters that you think, for parameters that you don't have data for, it'll allow you to propagate that uncertainty for those parameters into other parameters which you may have data for that helps you estimate them. Much faster computations than possible with original data if you use informative priors. And the most important one here is the last one, which says it allows you to incorporate the entire history of science. So it allows you to incorporate information on everything that's been studied on your question up until now. So if there's been a ton of research that's looked at the relationship between your data Y and your covariates X, whatever that relationship is, if it's linear or nonlinear, you can use that information, and it gives you a natural tool to incorporate what other people have done into your own analysis, assuming the system is similar. So in summary, they're a great tool, and why would you not use informative priors? All right, let's take a minute here before I go on to identifiability to ask a couple questions about priors and Bayesian inference. So I will give you a chance to ask any questions if you have any. If nobody has any, I'll just call on someone randomly to ask a question about priors. So let me give you a minute to think about them. All right. Any questions? This was usually if we're doing this in person, there's generally a lot of questions in this lecture.
I have a question.
Yeah, go ahead, Brian.
So let's say we're working in a system where there's been a lot of it's been well studied, and so we have a lot of information to inform our priors. That would allow us to use a prior that is relatively narrow or relatively specific, versus if we're working in a system where we still have some information, so we can use an informative prior. We would use a prior with a wider distribution. Is that kind of the difference there?
That's right. Remember when we were doing this example last week where we had sigma, we had a normal prior distribution for the maximum likelihood, and we had a mean of something like 35 and a variance of 4.85. It was this lab example in using priors in the maximum likelihood. Now, if we know very well that the mean of that distribution is 35, we can make that variance parameter very small. And the smaller we make it, that stronger that prior is. It's going to have more influence on the data. If we don't know it's 35, then we can make that variance very big. And even though we say the mean is still 35, when it has a huge variance, it could be anywhere between, let's say we say the variance is 10,000. So if we take the square root of that, it's 100. So it's the standard deviation of 100. That allows the variability in that distribution to range from, let's see, negative 35 to, what is it, 105, something like that. So a huge range in that variability. So you can make it as strong as you want, or as vague as you want. And let me just draw a couple pictures here. Okay. All right. Now, say we're doing simple linear regression where we have X and Y. And this could be the relationship between height and weight. And what we're trying to do with simple linear regression is figure out what the parameters are, beta 0, beta 1, and sigma squared. So I'm just going to write out the model first, the model statement. So our parameters are sigma squared, beta 0, and beta 1. So that's what our theta is in our Bayesian inference. Those are the three parameters we're trying to find. Theta given y, and theta are beta 0, beta 1, and sigma squared. Okay, so we collect some data. I mean, we can even say before we collect data, there's been a lot of studies on the relationship between height and weight. And we're pretty sure, well, let me hold that statement of our assertiveness on that. The relationship looks something like this, where we have beta 0 here, and then our slope is beta 1. Now, before we even collect data or before we analyze the data, we're going to have to think about priors for our slope and our intercept. Now, if we're very sure that when height equals 0, weight is right around here, this doesn't make a whole lot of sense for our height and weight example because height can't equal 0. But if we're very sure about our parameter, our intercept here, and we know it's somewhere close to here, if this spot here corresponds to this line here, and we want a strong prior, we can make our prior on beta 0 look like that. But if we're less sure about what it is, we can make our prior look like this. And then we can even go out to something that looks like that, right? Or we have no certainty where that intercept is. And we can do the same thing with the slope. If we know the slope is roughly 1, we can have a very strong prior around 1. And we can make it less and less strong by just making it not as tall, centered on where that value is. Now, when we collect data, that's going to feed into our Bayes' theorem. And then the prior, the posterior distribution will be a combination of what our prior is and what our likelihood of the data is given the parameter. And when we have a strong prior like this, the posterior distribution is not going to move around as much relative to the prior than it would in the case where we have this blue line here. So what we're going to do is specify prior distributions for our parameters. We'll say this is normal with some mean 0 and some variance sigma squared beta. So this is a different sigma squared than the one used for y. And maybe we'll say something different for this. And sigma squared has to be positive, so we'll use inverse gamma. With a shape and a rate. Now, the question, going back to your question, Brian, is if we have a lot of information on these, where do we incorporate those, or what does it look like? We incorporate them in these values here, in our means, in our standard deviations, or what are also called our hyperparameters for our prior distribution. And here. So now that we have a Bayesian model, well, I'm just going to move this down a bit. We don't have a Bayesian model yet. These are our prior models, or also called parameter models. And then we had a data model. So now this together is our model statement. We've added a level of complexity here. We've completed the Bayesian specification of our model by writing down our parameter models or our prior models. And if we had pre-existing information on what beta 0 is, what beta 1 is, what sigma squared is, and the uncertainty around that, we can incorporate that in here. When these values are large, we don't have very much information. When they're small, we have a lot of information. Now, when you're writing papers in journals or your dissertation or thesis, you are going to have to choose these values, and you're going to have to justify them. You'll have to put the citation in where you found that information. And sometimes the information won't come exactly in this format, meaning they might tell you what the mean and the variance was. Maybe they'll tell you the mean and the variance, and everything works out pretty well, but rarely do they give you a distribution for a variance parameter, or rarely is that reported in a non-Bayesian case. So you'd have to do something like moment matching to try and match the mean and the variance of these distributions to values that you observe in the literature. All right, before I go on, let me show you one more example. Any other questions about this? Okay, here's an example of where I've used strong prior distributions in the past. We had to, sea otters in Glacier Bay, Alaska have historically been counted using aircrafts where observers would fly along transects. They would count as many otters as they could, and then they would just keep flying. And they knew that they were missing some otters because of roughly 20% of the population's underwater at any one time foraging. So they developed a way to, let me just draw Glacier Bay, Alaska here. Here's the glaciers. This is the inlet of the Glacier Bay. They would develop transects, fly over these areas, count how many otters there are, and then they wanted to estimate how many otters they actually missed. So every once in a while when they saw a group of otters, let's say the plane's flying this way, and there's a group of otters here. Let's make them brown. Brown. Blue. They would deviate from their course and fly 5 circles around these, and then count how many they saw the entire duration of this flight. The reason they did 5 circles is because as long as it took them to do 5 circles, that's about the average dive length of a sea otter. So if they're underwater, they likely come back up, and they could keep track of them that way. And then they estimated how many they missed on proportion. And then they take that information and recalibrate the otters they counted in areas where they didn't do those circles. So if they flew these circles around this group of otters, originally they saw maybe 6 of them, let's say, but after flying the circles, they said, oh no, there's actually 10 of them there. 4 were underwater when we did it. We saw those 4 after we did the circles, and now we realized that we only saw about 6 out of 10. And they do this a bunch of different places and get an average number. And then they take that number and calibrate it to all the areas where there were sea otters, but they didn't do those circles around because they can't do the circles around them everywhere because they would run out of daylight. And it's actually pretty dangerous too. They have to fly very close to stall speed, which is not a great thing. And doing these 5 concentric circles is something they want to avoid. So one of our objectives was to try and get away from doing this concentric circle thing and this observer-based methods, and just use aerial photography. So they mount a camera in the bottom of the plane and then fly over, and then they snap pictures. But we didn't know, there wasn't a good way to repeat this approach here where they're flying in circles and counting them. But they've collected this data for I don't know, 10 years, and they have a lot of information on how many they missed. So we use that information, the average detection probability about, to describe a strong prior for how many sea otters are missed in aerial photographs. So here's the model we wrote out. It was something like YI are counts of sea otters observed in a photograph I. They come from a binomial distribution with some latent number of sea otters that we can't count exactly. We miss a lot of them because they're underwater, but this is what we're really trying to get at, this N, how many sea otters are in Glacier Bay. And then detection probability P. Now in our model, both N and P are unknown. We know what Y is, that's our data. So we could call this a data model. And then under that, we had a process model. Where, let's see. Ni is Poisson. With expected value lambda. And then log of lambda equals beta 0 plus beta 1 xi. And in our covariates, we had things like ocean depth, distance to shoreline, shoreline complexity, and what was the other one? The slope of the shoreline, the slope of the ocean floor. Things that we knew affected sea otter. So we collected data on that using geographical information systems and bathymetry layers. And we have our very familiar looking thing here. We have our linear equation. This has to be positive in this Poisson. This lambda has to be positive in this Poisson distribution. So we take the log of lambda, or alternatively, we take the exponent of both sides. And then this cancels, and then we just have the exponent of this equals lambda. All right, and then we had to describe prior models. So what are our parameters in this model? I've mentioned a couple of them. This is one thing we'll have to identify as the parameters and the data and the covariates. What are the unknowns in this model?
Hey, Perry, can I ask you a quick question?
Yeah, go ahead.
At the end of the statement where it says log lambda,
Yeah.
is that saying beta 0 again?
Right here? Right here?
No, at the end of that.
Oh, okay. Yeah, let me clarify that. This is, this statement here just means for however many covariates you have in your model. It could be, okay, so you got that part. You're just confused about the handwriting. I had just put D here for D covariates.
Oh, okay. I thought that was beta 0 for a second, and I was confused as why there was another beta 0.
Yeah, I just used D for, let's see, let's say J equals 1 to D covariates.
Oh, okay.
So we had like 5 in our model. So big D would be 5, yeah. Okay, so given that, Morgan, do you know what the parameters of this model are? What are the unknowns? Give me one or two of them, and what we're looking for are the unknowns.
Okay, I would say just beta 0, beta 1, first of all.
Yep.
And then would you include Ni and P in that, or?
Yep.
Okay.
Beta 0, beta 1. And let me just, instead of writing beta 0, beta 1, let me just do 1 for all betas and make it a vector. Okay, so that's 1 prior, and then you said n is a prior a parameter, an unknown that we need to estimate,
Mm-hmm.
and then p as well. Oops. P is a parameter.
And then lambda?
This is a good point of distinction here. Yeah. So is lambda a parameter? And the answer is yes and no. But if we include betas here, lambda is deterministically linked to this equation. So if we know betas, we know exactly what lambda is. And usually when we have parameters here that are deterministically linked, we just put priors on one of them. So we would just do priors on beta, because if we know beta, we know what lambda is. So we sometimes call lambda degenerative distribution of betas. But if we have this deterministic link, usually you just go down the line until you get to the parameter that will generate the value if it's completely known. So in this case, we'll use beta and not lambda. All right. So this was the model, and my point was, well, I'll get to a point actually. We can still go through this as an exercise. We've got these parameters. What are some distributions for these parameters we could use?
Hey, Perry, I just have kind of a question also because it is a Poisson distribution with lambda. Is that why we don't have standard deviation as an unknown parameter?
Yeah, well, do we have, let's say, do we have standard deviation in there? It's in there somewhere. Where is the standard deviation in that Poisson?
Probably in the beta prior.
Yeah, that's true. I mean, remember in Poisson,
It is lambda.
it is
right?
lambda. Yeah, the
Yeah.
variance equals the mean. So if we take the square root of lambda, then we have standard deviation. It's just we has the mean and the variance all wrapped up in the same parameter. And you said beta, and because beta equals lambda, yes, that's true. Well, if you know beta, you know what lambda is.
So then for the distribution of the betas, would it have to be positive like lambda?
For the betas, do they have to be positive? What do you think?
I feel like I want to say yes, just because like you wouldn't expect a negative rate here either.
Let me rewrite this equation here as lambda I equals the exponent of beta 0 plus beta 1 xi1. Does that help at all?
So isn't it that lambda has to be positive, but because we take the exp, the betas, they can be negative?
Exactly, yeah. The betas can be negative. Whenever we have this equation here, this linear equation, these betas can always, there always could be any real number. That's why we need the exponent to convert the negative betas to the positive lambda. They don't have to be negative, but they can be negative. Okay, so the betas can be any real number. How about a prior distribution for them?
You could go with normal, right?
Yeah, you could use normal. That's what I tend to use in linear regression or generalized linear regression. And the most common prior distribution for betas in linear regression, if you don't have any information, is to say something like normal with mean 0 and variance sigma squared equal to about 10, maybe 100. Pretty big variance. This doesn't look as big as it actually is. But when we set this sigma squared to 100 here, it allows beta to go basically between -200 and 200 with regularity. Like if we're simulating R norm, simulating in R from a normal distribution with a mean 0 and a variance sigma squared equal to 100, we would see values between about -200 and 200. Now, if you take the exponent, like we would do here of 200, that number gets huge. So this is actually quite vague.
Hey, Perry. So here you're lumping all of your different betas into one prior
Right.
model.
Yeah, that's a good distinction too. Just for simplicity, I could be more explicit about this and write them all out, and maybe I should do that. So was that the rest of your question, or do you want to follow up a little more on that?
Yeah, I guess I understand that for simplicity's sakes, that makes sense right here, but often you would be really interested in each one of those individually, right?
That's right, yeah.
Okay. Okay.
Also, not to belabor this a ton, but would we have beta like 1 through beta D basically because of the 5?
Yeah. Yeah, we would have one, we have a prior for each parameter in our model, but oftentimes we can simplify writing out the model if we have the same prior for multiple parameters.
Hey, Perry. I guess I'm just kind of confused, like, why are we picking distributions for these? Like, if we have the Sea Otter project you're talking about, and you said we had a lot of priors for that, so do we already have like a data set for those priors? And what if that data set violates like a normal distribution?
Yeah, that's coming up. So that's a great point, and we'll talk about that in a couple minutes here. All right, what about N? Let's see, N. Actually, we don't need a prior for N. N kind of has a prior. I mean, you could think of it kind of as a prior. I don't know if many people would, but it kind of has this prior here where it's Poisson lambda. It's not really a prior, it's more of a process, but it has a distribution. It's Poisson conditional on lambda. We'll see more about that when we write out the joint likelihood. Okay, now, any questions before I move on to P? Now, P is where we actually have information. We have data from the previous part. And to get to Morgan's point. Okay, so what values does P have to be?
It has to be between 0 and 1.
Right. What's a distribution we could use for that then?
Beta.
We could use a beta distribution. Yep, it's a good choice. Now with the beta distribution, we have a shape 1 and shape 2, or shape and a rate parameter. And this is where we said we had a lot of data from before with the Sea Otter study. And we want to use that prior information. If we don't, I will say if we don't have any prior information on P here, we won't be able to estimate both N and both P in this model. This is this identifiability slide that we'll talk about. It's on the next slide in our notes. There's a couple ways of getting information to estimate both N and both P. One is to collect data, multiple data sets here, multiple observations of Y in the same group. So this would be for a group of sea otters. If the plane was flying over the group 5 times, but instead of 1 observer counting how many sea otters there were there, you had 2 observers. And then they had 2 different values of Y here. That type of information would give us some ability to estimate the detection probability P. If we were doing something like distance sampling, where you walk transects and you assume that you see animals that are close to you, but animals that are further away, you don't see as well. And you have some detection function for P that looks like this, where this is distance. And you know what this function looks like. We could estimate P here. If we were looking at frogs in a pond, let me see, where's my eraser? And counting how many frogs were there, or fish, or whatever. If we go to a pond more than one occasion, and we get many Y values here for a single pond, then we can estimate both N and P. And this is the framework that occupancy modeling is built on. So occupancy modeling, if you're trying to identify occupancy and detection probability, you make these repeat visits. But with our sea otter stuff, with our airplane data, our aerial photography data, we didn't have multiple images. We just had one image over our transects. So we needed to estimate both our unknown abundance and our detection probability. And the way we estimate our detection probability was to use that information about how many sea otters are underwater at any given time. And from those data, we got a mean and a variance of how many sea otters were underwater at any one time. So then how do we parameterize this distribution here, this beta distribution? Let's see, pencil died. In the beta distribution on the bottom, we have a shape and a rate for our detection probability P. Well, we know on average what P is, and we know what standard deviation of that is. So to fill in our shape and our rate for a prior distribution, we do the moment matching we talked about before. So we take our mean and our variance, and then we get our shape and our rate parameter for our detection probability P. And if we have a lot of data on that, we should have a mean, and then we should have a pretty precise standard deviation. And then we can plug that prior information into our P value here, and it allows us to estimate our data, both N and P. And P is going to look just like the prior distribution because we don't have any information on P. But because we know we have an idea of what the distribution of P is, it's also going to allow us to estimate this N value here with the appropriate uncertainty accounted for in the P. So we could do an exercise and say, well, what if the mean of our detection probability P is 80%, and there's a variance of about 0.05 on that? Well, we would do what we did in our previous labs. We would take that mean and that variance, figure out those equations for the beta distribution, figure out what the shape is and what the rate is, and then plug that in as our prior. How would we make this beta distribution vague?
Do you set the variance higher so that the prior has less influence?
Yeah, essentially, yes, you set the variance higher, but there's a unique property of the beta distribution. When the shape equals something and the rate equals something, that it becomes a uniform, essentially a uniform distribution between 0 and 1. Anybody remember what that was?
Isn't it when they equal each other?
And when they equal 1, yes, they both equal each other and they equal 1. So if the shape equals 1 and the rate equals 1, the beta distribution is a uniform distribution between 0 and 1, meaning that all values between 0 and 1 have equal probability, which means in terms of our detection probability, P, we're saying it could be anything between 0 and 1. Any value is equally likely. So that's the case where we use strong priors to estimate P. Now going back to our slides, the benefits of using informative priors. In our case, it definitely reduced problems with identifiability. And I'll talk about that on the next slide, but it's that N and P. And N and P become unidentifiable when you don't have enough information, because as P gets smaller, N gets lower, and as N gets lower, P gets higher. They trade off if there's not enough data. It allows estimation of quantities that would otherwise be inestimable. So this allowed us to, by using the strong prior on P, well, by using a prior, not a informative prior on P that accounted for previous data and uncertainty in that estimate, we were able to estimate the abundance N. And then it allowed us to incorporate the history of this survey area in Glacier Bay. Our information on the natural history of sea otters that we had obtained from previous data. Okay, has anyone heard of an N mixture model? Yeah, that's what this model is. This is an N mixture model. And it's this N is the N, it's the N mixture because we have this Poisson distribution and a binomial distribution. So this was first published for ecology data in 2004 by Andy Royal. Okay. All right, now let's talk a little bit about identifiability. Any questions? Let's see where we are. All right, so identifiability, a model is identifiable if it is possible to learn the true values of this model's underlying parameters and latent quantities based on a large number of observations. Different values of the model's parameters must give rise to different distributions of the data. Non-identifiability occurs when parameters can trade off and produce the same distribution of the data. Let me give you an example from the sea otter stuff I just talked about. All right, we had data here. These are count data, counts of sea otters at site I. And we're trying to estimate these two parameters, Ni and P. So let's take a look at this. Let's say our counts are 100. So we observe 100 sea otters, and then we're assuming this can come from a binomial distribution with a mean of N and detection probability or probability of success P. Now there's a lot of ways this 100 can arise based on the parameterizations of the N and the P. For example, if N, the true value of N equaled 200, then we would expect P to equal 0.5. Alternatively, if the true value of N was 400, then we would expect P to equal about 0.25. And there's this relationship between N, whereas N gets larger, so let's say 0, and this is, I don't know, 500, and P, where this is 1 and 0, as N gets larger and P gets smaller proportionally, we're still going to observe the exact same types of data. So if there's a ton of animals out there, but the detection probability is really small, we'll observe the same type of data there as we would if there were a reasonable amount of animals there and we had a high detection probability. So together, these two values, the relationship between these two, are all going to give data that's roughly the same. Let's say 100. So if we're only observing the data here, if we're only going out and counting how many sea otters are there without knowing anything about the detection process or how many sea otters are truly out there, N and P could be anything. I mean, if N's big, P will be small. If P's big, N will be smaller. This is the idea of identifiability where they trade off. So in order to figure out exactly where N is on this list, on this area, let's say if it's in somewhere in here, we would need to know something about where P is as well. And because we can use our prior information about P on the sea otters, what the detection probability is using information from their life history, and we know it's somewhere around here, then that can help us out estimating what the true value of N is, given the data. Because we're still observing data here, our Y. So this is our Y. We're still observing that. And although there's a trade-off between N and P, if we can constrain our value of P, that'll give us the best estimate of N. But if we don't know anything about P and we have these two parameters, N and P, we're trying to estimate both of them, they're not identifiable because if one's big, the other one would be small. If one's small, the other one would be big, and so on. They both can produce the same types of data with lots of different combinations of N and P. Okay. So any questions about that? When we-
So,
Go ahead,
sorry.
James.
Okay, so the identifiability is trying to find the true combination of N and P that is generating the 100.
Yeah, if you can find the true combination, then it's identifiable.
Thank you.
Yeah. And we'll be able to see this in some models. When we look at the MCMC trace plots. So trace plots show us, this is an example of a trace plot, let's say for beta 0. There will, in our MCMC sampler, we're going to get something that looks like this. You may have seen this in Bayesian textbooks where you have a fuzzy caterpillar looking diagram here. And what this is samples from the marginal posterior distribution of beta 0, and it gives us all these values of beta 0. And then from these data, we can make a histogram to figure out what beta 0 is. So this axis here is the same as this axis here. And when we see models that aren't identifiable, what we see is trace plots that do this. So if we have beta 0 here and beta 1 here, if these two weren't identifiable, or we could say if this is N and this is P, we know those two aren't identifiable without additional information. We see plots that look like this. And then the parameter that's trading off with it does the exact opposite. So as one goes up, the other one goes down. And you can imagine with N and P, if it's trying to get the value close to 100, based on a combination of how many animals are out there and what the detection probability is, then as N goes up above 100, P is going to drop below 1. And then, yeah. Okay. So that's identifiability.
Harry, is identifiability only a concept for the parameters in the data model, or is that also an issue with parameters in the prior models?
It could be
And the process models, not prior, sorry.
It can be in the process model too.
Yeah.
Data model and process model. And then describing prior models help with identifiability. Yeah, and there's a much simpler example of identifiability too. Let me say, let's do this. If we have A times B equals 9, we have one equation and two unknowns. We don't know A, we don't know B. So A and B are not identifiable. We don't have enough information. A could be 3 and B could be 3, or A could be 4.5 and B could be 2. We need a little more information about B to figure out what A is. That's like we need a little more information about P in our detection model to figure out what N is. And if we have some prior distribution on B, that would help us figure out what A is with the appropriate uncertainty. All right. Okay, priors. So why are informative priors not used more often? And there's a lot of cultural reasons for this. This goes back to Fisher's dislike for Bayesian inference, and that all studies should stand alone and be equally convincing to all rational minds, is what he stated. Current texts that we use mostly use vague priors. It can be hard work to incorporate information into our models. We will have to justify our choice of using informative priors. And sometimes it's easier to just say we'll use vague priors instead of strongly informative priors, even if that information exists. And then there's this idea of excessive subjectivity in that priors may influence our posterior distribution. I've got a signed copy of, let's see, do I? Yeah, so I have a signed copy of this book here. And it says, Thanks for all your help with this book. May all your priors be strong, from Mevin and Tom. So they're proponents of strong priors as well. Okay, how to develop good priors. Strong scholarship is the basis for strong priors. So when we talked about our diagram, our line of inference, where we had current concepts, theory, and hypotheses that led into data collection and modeling, and then new inference quantified by uncertainty. That first box is our strong scholarship for choosing good priors. Another area is if you can do pilot studies, you can use the data from your pilot studies to incorporate that into your analysis after you do the complete study. There are a lot of theoretical equations in ecology that describe the relationship between two states of interest. So one example would be allometric relationships in biology. Using the theory, ecological theory as a basis for describing informed priors is a good source. Okay, so how to develop them. We can build deterministic models with parameters defined by processes. And then like I mentioned with the beta distribution in the sea otter example, we often need to use moment matching to convert means and standard deviations into shapes and rates for prior. So that's pretty common practice. You'll usually have to do that. Okay, this came up a little bit last time when we were talking about, let me see where we were doing at time. I think I wanted to get to, okay, I want to get through these next few slides. Do we need a break or should I carry on through? No break, okay, all right.
Can I ask a question? No.
Yeah.
Your prior slide. Are often times when people use informative priors, they're using data, they're using means and standard deviations from a prior data set?
Yeah.
So that's considered a strong prior.
Yeah, if it influenced, well, yeah, this is, so it's on a continuous scale how much your prior is going to influence your posterior distribution. And is it a strong prior or a not strong prior is two discrete categories that we're trying to bin this continuous scale into. If your priors influence your posterior a lot, then I would say it's a strong prior. And if it doesn't influence your posterior distribution, it's not a strong prior. So what I did there was just pass the buck down to making another category saying a lot and not a lot. So strong prior and non-strong prior is a lot versus not a lot.
But in both cases, those are informative priors.
Yeah, they are more informative than others, yes.
Okay.
If you, let me see if this next example is. Yeah, and I can try and address that question based on the relationship between our posteriors and our priors here. So here is an example in the top left part of this graph where our prior is the red line and posterior is a black line. We sat down, we developed a prior, and we then collected some more data, and we fit our Bayesian model, and the posterior looked exactly like the prior. We didn't learn anything new here. We just confirmed what we already knew with our prior distribution. Now, to get to your question, what is an informative and what is a so-called non-informative prior depends on how much the prior moves this posterior and what this posterior looks like compared to prior. So is it considered informative prior? I would say if you use information from a study, you're definitely increasing the information in your prior compared to if you just chose a distribution centered at 0 with a large variance. You can use information from a study. Let's say, for example, let me share my screen. I'll see if I can make this a little more coherent than rambling. All right. Well, you think about a simple linear regression model. Yi comes from a normal distribution with mean beta 0 plus beta 1 xi and variance sigma squared. And then we have to develop our prior models. So we have beta 0, beta 1, and sigma squared. Now we're going to say these come from a normal distribution. Oh, that can't be normal. Okay, now the question is, we're looking at the relationship between height and weight. We have some information from previous studies on what our slope and what our intercept should be. And we would incorporate that information here, 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 and here. Now in this particular model, if we take this beta 0, we take the study information from that study and say, well, beta 0 should really be about 6. Now we're using that information from the study there, but if we don't know about the uncertainty in that relationship, then we might just say, well, this is, because we don't know anything about the uncertainty, let's say sigma squared equals 10,000. So now we're using information from that study, but we're kind of offsetting it by this uncertainty parameter. We're saying there's a lot of uncertainty in this value. So even though we are using some information from that study, it's still a pretty vague prior. And same thing if we did this, if this was like 1.5, but we don't know about this number exactly. We don't know what the mean is exactly. So again, we're going to say sigma squared equals 10,000. So we're centering in the right spot, but we have so much uncertainty in this model, it doesn't really matter, and it's still a very vague prior. And I think reviewers would look at this and be like, okay, that probably doesn't influence, that's probably not going to have a big, that choice of prior is not going to have a big effect on the output of your analysis. It's pretty vague. But if I go in and say, well, actually, we know that the uncertainty is associated with this. We're pretty sure that the intercept for this line on the relationship between height and weight is 6, and the variance of our uncertainty is something like 0.001. And same with here. Now we're saying we have a very strong prior belief on what that slope is and what that intercept is. And that's definitely going to influence our results, our new data. And maybe it should, because maybe we have been collecting information on the relationship between height and weight for 200 years, and we've got a pretty good idea on it. And we don't want to go out and collect 10 new samples and come up with something completely different on what that relationship is. Now, if you choose very strong priors like this, you're going to need to justify it to your reviewers, your committee, or the people who are peer reviewing your manuscripts. And the way you do that is by citing those papers, describing exactly what these values are and what your justification was for choosing those values. Now, to make one more point about your question, Angela, is what you can always do is fit your model both with strong priors and more vague priors and see how much influence it has on your data. And if it has a lot of influence on it, then you know that those choice of priors are influencing the results. And then you need to think about then think about the rationalization for that choice. If it really makes sense, or if maybe it was 2 studies conducted in 2 different areas and maybe it's not the same system, something like that.
That's super helpful, Perry. And can I just ask one more question?
Yes, please.
We can move on. But what if you have a prior, like a variable that you're interested in, that variable is just associated with tons of uncertainty, like one experiment's doing this, another experiment's doing this other thing, and it's sort of all over the place, but you use it as a prior, and so sure enough, it would be informative because when you put it in, it's changing the results compared to a non-informative. But it's this like crazy variable that is a little bit I guess has some unpredictability associated with it. And I mean, in that case, it wouldn't seem like that is a good choice to use informative priors.
Yeah, what is this variable? Maybe we can write out this model and.
You want me to?
Well, you could just can just tell me a little more about it.
Oh yeah. Okay, so this variable is a enzymatic rate.
Okay.
You're getting an enzyme activity, and it's in the form of a slope, a rate.
Oh, okay.
It's just like bonkers. It's all over. Like one experiment it does this, and the other one is doing this other thing, and it's just highly variable. So in that case, it seems like why would you use something that's?
Yeah, if you probably want to capture that uncertainty and that unknown, what's going on in that parameter by using something that has uncertainty associated with it. So if it was like a slope in a linear regression model like beta 1, you would want to make that variance of that beta 1 prior pretty big to capture that variability. Yeah, if you knew more about why it was doing certain things, then you could maybe parameterize it a little differently. But because it seems to do these different things and it's crazy, then you probably want to have enough uncertainty to cover that variability. It would be interesting for you to write out that model and talk about it, and we could follow up with it, just see I get a better picture of what's going on.
Yeah, I could try that.
Okay.
Yeah, okay. Thank you for answering questions about that.
Yeah, I don't know how well I did, but I think if we followed up with it, we could do a little better job. Okay. All right, so what you can do in when you present posterior distributions of your parameters is show both your prior and your posterior. And that way it shows how much you've learned relative to what your prior was. And in this case, we learned nothing new. The data confirmed our expectations in our prior. Here we have the mean. After we collected our new data set, the mean moved to the right a bit. So our parameter theta, what we thought it was over here, it appears that the data actually suggests that the parameter value is a little higher. And then there's also this word shrinkage here, which means it got small. The width of that posterior distribution got narrower, meaning we tightened up the uncertainty about what we knew about that parameter. Here, in this case, we're still centered on the exact same spot as our prior distribution, but we gained more information about it. We became less uncertain about the width of that distribution. All right, now in this last case, we collected data, and our data showed us that actually we were more uncertain about the parameter than we were before. So maybe we were a little too optimistic when we chose our prior distribution. That could be one reason for seeing this. We chose our prior distribution kind of erroneously, and maybe should have thought about it a little harder. The other thing is maybe the system has changed, something like climate change, where we're looking at 100-year event, the occurrence of 100-year events or something like that. And where we thought things happened about every 100 years, now we're figuring out, well, maybe it happens much more often than that, but we also just don't know. All right, so we can always show these plots of our marginal distributions of theta for both our prior and our posterior in our analyses or in an appendix. All right, how do you present informative priors? You could do this in a table. So this is from, I think, a paper on Yellowstone bison and brucellosis transmission. Yeah, there it says in the table, brucellosis in the Yellowstone bison population. So they have this fairly complex model that they are modeling transmission rates of brucellosis. And they have these parameters here that correspond with rate of transmission, number of offspring recruited per seronegative, female number of offspring recruited per seropositive, female, and then number of offspring recruited per seroconverting. And they describe exactly what their prior distributions were. So we have rates here, so we see beta distributions, and then we have transmission is somewhere between 0 and 50 with a uniform distribution. And then they describe what the mean of those distributions were and what the standard deviations of those distributions were. And then how those means and standard deviations that came from these papers factor into the moment matching of the beta distribution. So this is another paper that talked about number of offspring recruited per seronegative, seropositive, and seroconverting. That was described in this previously published paper. They used this information from this paper to describe their prior distributions on these parameters, and that's how they reported those in this manuscript. And this was, I think, Ecological Monographs. And then again, you can show what your prior distributions are along with your posterior distributions. Here, the dotted lines are prior distributions and the solid lines are posteriors. This is what a vague prior would look like. It's very wide, very flat. And then you see the posterior. These are the results from that previous example here. Okay. Vague priors. So I tend to use the word vague instead of non-informative. You hear both used a lot. Non-informative is a bit of a misnomer for priors because at a minimum, you're describing what the support of the parameter is. So you're providing some information. So all priors contain some information no matter how you parameterize them. So I tend to avoid the word non-informative. A vague prior is a distribution with a range of uncertainty that is clearly wider than the range of reasonable values for the parameter. So this comes from Andrew Gelman and Jennifer Hill's book in 2007. It's a black book with gold writing. People also call them diffuse, flat, automatic, non-subjective, locally uniform, objective, and then incorrectly non-informative. This last point here, the best way to make a prior vague is to collect lots of good data, is because when you have a lot of good data, that is going to outweigh the influence of your prior distribution. Let's see, okay. All right, so and this goes back to a comment I made earlier about describing whether priors are vague or not. There's kind of two approaches here. We have operationally provisional, where you try a prior. Does the output make sense? Are the posteriors sensitive to ranges of the parameters? Are the values of the posterior, are there values in the posterior that are simply unreasonable? If so, we may need to try another type of prior, or you could do strategically provisional, where we use vague priors until we can get informative ones, which we prefer to use. So this would be like a pilot study. If we collect some information on the system, once we have that information, then we can make vague priors. You see both of these approaches reported in literature. So one thing that you may or probably will be asked to do at some point in the future is review other people's work on Bayesian inference. And you'll recognize these two approaches that people use for choosing their priors, where they start off with vague priors, and they see if things they're sensitive to the data, and if they are, they try something else, and they do something essentially until it makes sense to them, and then they report on that. And the other one is understanding that priors can be good and informative. You have to use them right, and if you can't use them right away, start off with vague priors, and then move towards more informative priors as you collect the information. So you see these approaches a lot. Okay, this is a vague priors need to be scaled properly, and this is a common error that we see in when reviewing manuscripts. So this is kind of an important topic. Let me show an example with R. I'll start off with this example. Suppose you specify a prior on a parameter theta, and maybe theta is from a linear regression model, or generalized linear models where this happens. Let's say theta comes from a normal distribution with mean mu equals 0 and sigma squared equal 1000. Will this prior influence the posterior distribution? And there's two ways it can. One deals with this idea of scaling. The other deals with transformations. All right, so what do you think? Do you think a theta coming from a normal distribution with mean 0 and variance equal to 1000 is going to influence the posterior? What if theta is measuring distance, for example, distance to road or distance to car, distance to deforestation?
Well, it would depend on your units, right?
Right. Yeah.
If your units are centimeters, then maybe you need a bigger sigma squared.
Exactly. So we have to scale these priors to match the units. Is one key thing to keep in mind. And we see this a lot with distance. Sometimes just incorrectly coding things, like if units are in meters and kilometers, you have to be aware of that type of unit. So we have to scale those properly for the units that we're talking about. The other one, which is probably a little more interesting and much less obvious, is when we, and I might get to this later too, but it just jumped out at me now, and this is kind of an interesting question. Okay. Let's say, actually, I'm going to switch back to the whiteboard and draw out a model first, and then do a simulation. And this is choosing priors that go through transformations. How are we doing on time? Now in our, let's do two models. We have simple linear regression. And for this problem, I'm going to choose 10,000 here as the variance for our intercept and our slope. I'll use the same distribution. And in this case, I'm going to say this is going to be a non-informed, vague. These are vague priors. Let's assume the units are right and everything. Let me draw out another model. And this is going to be logistic regression. The parameters in this model are beta 0 and beta 1. P is it is a parameter, but if we know beta 0 and beta 1, we know what P is. So I'm just going to write beta 0 and beta 1 in the prior models. Okay, so we have two models. We have simple linear regression and then logistic regression. In the first case, this is a vague prior. These are vague priors on beta 0 and beta 1, assuming the units are on the right scale and everything. In this case, these are very informative priors. Let me show why. And this is something that was there were books on Bayesian inference that in this model recommended these priors as vague priors. So people had made this mistake for a long time. But if we look at what happens, let's sample some data. Let's say I'm going to make a for loop. I'm going to do 1,000 samples. And on each iteration of my for loop, I'm going to sample a value for y. From this model, beta 0 plus beta 1. I'm just going to say x equals 1. And complete this model. All right. Sigma, I'm just gonna say equals 1. Now I'm going to sample beta 0 and beta 1 from their prior distribution on each one. After I sample those from their prior distribution, then I'm going to sample Y, and then we'll look at a histogram of Y. Let's see if that worked. Okay. So we expect values with these prior distributions on these parameters and simulating from our normal model, anywhere between -400 and 400. So that's pretty vague, depending on what the units are. Okay. Now, if I take these same priors and put them in a different model, a logistic regression model, where I have to do this nonlinear transformation. Forgot exactly where these go in our binom. 1P. Y is, what is Y? Y is all zeros. And let's look at P. P is either 0 or 1. And this is all because of our choice of these what we thought were vague priors, because that was the same form we used in the normal. It turns out what happens is when you have huge variability in your beta zeros and your beta ones here, and it goes through this nonlinear function, P is always going to be either 0 or 1. So that's hugely informative. And this is saying we should either observe all, let's see, a probability of success very close to 1 or very close to 0 and nowhere in between. Ideally, if we wanted a uniform distribution on P, this would be filled in for all values of P. It would be equally likely for a prior value. But now it's saying we're putting all our prior weight on 0 or 1, the extremes. So how would we choose a prior so we get P that looks like a uniform between 0 and 1? Well, it turns out if we do about 1.4, that gives us something close to what we're looking for. Still a little informative. Maybe 1.5. A little better, still a little more weight on P, but we have to look at this transformation, the inverse logit function, of our prior values to see how much influence they're actually having. So a better uninformative prior for in the model we showed is, instead of using 10,000 here, we use something like 1.5 squared when we have logistic regression. Okay. This just talks about units for scale. Let me see, I'm not sharing. I just have 2 more slides here I want to cover. All right, so scaling, we talked about scaling and how we need to scale our standard deviations on our parameters to the appropriate units. Okay. So what I just talked about with that logistic regression function is this last point. When we have nonlinear functions of parameters of vague priors, they actually do have informative priors. If we use vague priors, oftentimes we'll have problems in our MCMC sampler, so we'll want to use informative priors for that. They can cause pathological behavior in posterior distributions, including values that are unreasonable. So we see this sometimes in survival analysis, where we know survival would not be 0, for example. All right, sensitivity. Changes in parameters of vague priors meaningfully change the posterior when data sets are small or have high variance. So if you have a data poor system, small changes in your vague priors are going to influence this. I think this is as far as I wanted to get today. Yeah, so we'll stop here. We'll start on this next time. We've been going for a bit longer than I wanted to. But if we have any questions or you want to see any more examples, I'm happy to stick around for 20 minutes and talk about this too.
Yeah, Perry, I was wondering if somebody has something more pressing, please take over. But I was wondering if we could go over the detection probability model a little bit more, because I have questions about, I don't know, almost to the extent of like dealing with, yeah, I don't know how to explain my question yet. But
yeah, we can go over that some more. I forgot to make one comment too. In the EECB colloquium on Thursday, the speaker was talking about state space models. And that's something you hear a lot too, state space modeling. So state space modeling is just another word for hierarchical modeling. And you saw that in some of the slides where there was process models and data models. And he was talking about those things in a very similar way to how we talk about them here too. And if you're interested, we could try and look at that paper and decompose that model as well, just because there's an application behind it too. And sometimes it helps to put these applications that we see elsewhere into the theory that we learn here. But there's a lot of these different names for hierarchical models. State space models is one of them. Hidden Markov models. There's some debate about what are they called? SDMs.
Structural equation model?
Exactly. Yeah, that's what it was. Structural equation models. To me, I look at a structural equation model and it's just a hierarchical model. I think people who are on the camp of structural equation models say the opposite, that hierarchical models are just a structural equation model. But anyway, we use hierarchical models to describe all these other things that have different names. Okay, so detection probability. Did you have a specific application that you're thinking of, Mia?
Well, yeah, it's very personally motivated for my
That's fine.
for the pika work because they're hard to detect and in the Great Basin, they're lower elevation, they have larger home ranges and they're less of them. There's less density and so the detection probability is an interesting question that I'm going to be looking at and comparing it with data from the national parks that they've done some detection probability and then I wonder like are these comparable because they're going to be in completely different areas and
Mm-hmm. Okay, so are you trying to detect the species or individual animals? Like, do you care if you see one pika from, I mean, if say you named them all, right? Do you care if you detect pika 1 from pika 2, or do you just care if you see a pika at a site?
right now we just care if it's the site's occupied.
Okay, so you're looking at just species occupancy. Yeah, let's write out an occupancy model. These occur across all fields. Wildlife ecology, plant ecology, entomology, detecting threatening people at airports, things like that. So these models are used everywhere. Here's what it looks like if we write out so I'll write out the occupancy model. The idea behind an occupancy model is you have some study area or study system that you can break into units.
Oh, we're still looking at the slides.
Oh, okay. Thank you. Okay. And you randomly sample some of these. You visit those sites. And if you detect whatever you're looking for, it's a 1. If you don't detect it, it's a 0. And you're going to go back to it more than one time. Because you know that if you go there once, it might be there, you just don't detect it. Essentially, there are 3 outcomes. Let's say you go to a site on time t equals 1 and time t equals 2, and we have 3 sites, I equals 1, 2, and 3. If you go there and you observe it, the data look like a 1. Let's say in the first site, we went there the first time, we observed a pika, and then the second time we went there, we didn't observe it. At the second site, we went there 2 times and we didn't observe it at all. Same with the third site. So we only saw something here on the very first visit. We know that there's going to be 3 possible outcomes for our data. First, let's make an assumption of this model. The assumption is we're going to go here twice, but the system is going to be closed to movement in and out of our sites on 2 different occasions. So if we go there, our first visit is March 1st, and our second visit is March 8th, that if this site was, if there was what we're looking for in this site, it's going to stay there. Or if we go and look in this site and what we were looking for wasn't there, it's going to stay that way. It's going to stay unoccupied. Okay, so that's assumption. It's called closed to movement. There are three possible outcomes for our data. We can observe it. Let's say we observe it. Then we know it's there. If we observe an animal there, we know it's going to be there. So it's there. It's truly there. And we see it. The second possible outcome is it's truly there, we just don't see it. We failed to see it. So this is like we're flying over sea otters and we take a picture and nothing shows up on the surface of the water, but that's because the animal was actually underwater and we didn't see it. Or you go to look for pika and it's really there, but you just never found it. It was hiding from you. And the third option is it's not there. And if it's not there, you would never see it. You see it, you don't see it with probability 1. All right, we're going to use some notation here to distinguish between these three possible events. Our data are this. Here's y for site I at time t. We're going to say our y is either a 0 or a 1 at time t is going to come from two possible scenarios. This is our first introduction to what's called a mixture model. Not a mixed model, like not a generalized linear mixed effects model, but a mixture model. And basically all the models used in at least wildlife ecology are mixture models. We see mixture models when we have this bracket here, this big bracket, which I'll describe in a little more detail. All right, now here's how we're going to draw our three cases. An animal is either going to be truly there or truly not there, and we're going to represent that with zi. If it's truly there, we're going to say that equals 1. If it's truly not there, we're going to say it equals 0. We aren't going to know all of our values of z. It's this latent, partially observable parameter. We're going to know some of them, but we're not going to know all of them. We're kind of playing like we're an oracle and we can see the truth. And z is the truth. All right, so when the animal is truly there, when zi equals 1, we're going to say we're actually going to see it with probability p. Okay. And when it's truly not there, yi is going to be 0 always. It's going to equal 0 with probability 1. Now what we observe are the data. So we observe this. What we're interested in is the z's. We want to know if a spot is truly occupied or not, or what's the probability that it's truly occupied. So we're going to have another model. So this would be our data model. Now we're going to have a process model that's going to describe our Z's. Zi, we're going to say, comes from a Bernoulli distribution with occupancy probability psi I. Now notice ZI does not have a T on it, and that's because it's our closure assumption. We assume that if it's there, it's going to be there for time period 1 and 2. If it's not there, it's not going to be there for time period 1 and 2. So it doesn't depend on time. We're assuming the population is closed from time 1 to time 2. Y, on the other hand, can be, it does depend on time because it can be a 1 one time and a 0 the other time. So we need that T subscript. With Z's, we don't. That's because we're assuming it's closed. So Z, I said, was a partially observable latent variable. Let's write out what Z might look like for this one. All right, so this is Zi. And we have I equals 1, I equals 2, and I equals 3. What is Z for I equals 1?
Z would be 1 for that.
Yeah. How did you get there, Morgan?
Because if we assume that the population is closed and we saw it at one time period but not at the other, we know that it's still there because it hasn't been able to leave.
Right. Yeah. So Z is, we saw it there, so we know it's there, right? So Z is whether it's truly there or not. And on the first visit, we saw it was there. So, okay, we know that it's there. That's the easy one. What about I equals 2 and I equals 3? What is Z for those ones?
Zero.
Why do you say that, James? Follow up with that.
Well, it would be 0 because, well, I guess it doesn't have to be 0, but I was thinking because both times we don't detect anything being there.
But it's confusing because in 2 it's truly there, but we didn't see it, and the oracle, we got it wrong as the oracle, right? So
Wait a second. Did I say in site 2 it was truly there? Oh, these are the 3 cases. So there's a little confusion that these actually correspond with these. Okay, I see. It actually works out that they do, but I equals 1. These ones I didn't mean to necessarily correspond with site 1, site 2, and site 3. I just used 3 as an example because it was easy to draw quickly. And it kept it simple, and it happened to correspond with there's 3 outcomes. But now that you said that, it does work out that the way I developed this problem is 1 does correspond with 1, 2 does correspond with 2, and 3 does correspond with 3. And if I had a little foresight about a minute and 30 seconds ago, I'd have been like, oh yeah, I developed this example to correspond exactly with 1, 2, and 3. But it just turned out that it does. Okay. All right, so let's go with what Mia said and say this corresponds with site 1, this corresponds with site 2, and this corresponds with site 3. All right, so it is truly there, but we fail to see it. So in this case, we didn't see it, but we were saying that it was truly there. So Z would equal 1 if we were an oracle and we could see that thing. But in reality, we're not. And we don't know what this is. We have to estimate it. It's a random variable. It's one of these parameters. It's one of these unknowns in Bayesian inference where we don't know what it truly is. And we treat everything we don't know as a random variable. So we're going to have to estimate not only the second site, but the third site because we didn't see it here. And if we don't see it, it can be 2 possible things. It can be truly there and we just didn't see it, or it could be not there and we don't know. And we treat this unknown value here as a random variable that we'll sample. We know what this one is because we saw it. We know it's there. We know that z equals 1 because we saw it. Whenever we see it, we know that it's truly there. It's just, so there's no issue with that. The only place where there's issue is when we don't see it, there's two possible outcomes. It could have not been there and we would never see it, or it could have been there and we just didn't look hard enough. Okay, so that's what that's a little bit more about z. I'm going to finish writing out this model. We can say the logit of psi equals beta 0 plus beta 1 xi. And then we could add covariates to affect our occupancy probability. We can also say the logit of P equals, instead of beta, I'll use alpha. Alpha 0 plus alpha 1 W1. All right, so now we have covariates that may affect our detection probability, maybe weather, wind, things that make it harder to see a pika on an individual day. And we also have covariates that affect where pika actually are. So things like habitat quality. And then with our priors, our priors in this model are beta 0, beta 1, alpha 0, and alpha 1. It would be tempting to say, what about psi and what about p? But remember, if we know, because of this equal sign here, if we know beta 0 and beta 1, we know what psi is. If we know alpha 0 and alpha 1, we know what p is. And we'd probably say these come from a normal with some mean and some variance. All right, so that's the occupancy model in a Bayesian hierarchical framework. Data model on top, process model, and parameter model on the bottom. We can write this out as another step. Let me write this out as the joint distribution of the parameters given the data. Okay. So that would be how we write out it's close to how we'd write it. We'll talk about indicator variables and writing that out later. But this would be how we'd write out the posterior distribution parameters given the data. And we see it's hierarchical because we have this ZI on the left-hand side of the conditioning statement and on the right-hand side of this conditioning. Okay. Any other follow-up questions on the occupancy model?
I have like a ton more questions, but we're out of time, so I'm gonna like email them to you or something.
Okay, sounds good. Yeah, and we could talk more about it at the beginning of class on Wednesday too. All right, I will post lab 4. I'll post groups. I'll post a snapshot of groups, and yeah, and then I'll see you on Monday. All right, Wednesday. Okay, bye.